in a couple of different contexts. So we're going to talk about changing variables in the context of multiple integration. So I just want to kind of remember and kind of relate this back to what we did in Calculus 1. So when we used U substitution. So in U substitution, we used U substitution for integrals where we had integral from, I'm going to say, a to b of f of x dx. Back when this was the only kind of integral that we did, and we said that x was some function of u. So to evaluate this integral when x was some function of u, we did our U substitution, and we said dx, we had to find our dx, is, I'm going to say, g prime of u du. And I could also write this as dx is dg du times du. So when I substitute this back into the integral, this is just a kind of a more of a technical way of talking about U substitution. We said that our integral becomes of f of x dx from a to b becomes the integral from, I'm going to say, c to d of f of g of u, and then our dx is dg du. And our limits, this comes from changing our limits from being in terms of x to being in terms of u. So this is U substitution, a more formal way of talking about U substitution. We can make a similar kind of substitution for double or triple integral. So when we're doing multiple integration. So we can have, I'm going to say similarly, for double integral, we'll just talk about double integrals here. The double integral over some region R of f of xy dA that we've been working with almost the entire chapter. We change the variables. If we say x is some function of u and v, and y is some other function of u and v. Our integral becomes, and we'll say this without, I'm not going to show where this comes from. I wrote on the board, on the sideboard there, Calc III 2013 14.8 supplement. I go through kind of a motivation for where this comes from, but we're not going to talk about where it comes from here. So our integral becomes, if we make this substitution, r of f of xy dA becomes the integral over some new region S of f of g and h, which are functions of some other variable, times this quantity that's related to this dg du. We get the partial of x with respect to u times the partial of y with respect to v minus the partial of y with respect to u times the partial of x with respect to v. du dv. So when we make this substitution, when we let x be some function of u and v, and y be some function of u and v, when we make that substitution, this integral becomes this quantity. Very similar to the way that when we did u substitution, our integral became this quantity, and this dg du we had to take into account when we do this integral. And S is our region after we change the variables. So we get a new region after we change our variables. This factor, this absolute value of these partial derivatives, is called the Jacobian. So it gives us a way of making a substitution, change of variables, and evaluate our integral with respect to different variables. So we call this the Jacobian of x and y with respect to u and v. That's why we named our section the Jacobian. So we write this Jacobian, we give this a symbol so we don't have to write out this quantity. So our Jacobian is written dxy over duv. And if we go back here really quickly, if we look at this form, this is in the form of a determinant. So this is a determinant of a 2 by 2 matrix. So we have a determinant of our partial derivatives. So this is the determinant of this matrix, dx du, partial of x with respect to u, dx dv, dy du, and the partial of y with respect to v. So this is our Jacobian. We'll see this symbol. This is how we're going to find it. You'll also see it written. You'll also see it written in some places as j of t of u and v, or just j of uv. And the way we think of this, so what we're doing when we change this variables, we're making a transformation. That's what this T stands for, transformation. We're making a transformation from the xy plane to the uv plane. And one example that we've done these conversions before, we didn't think of it as a transformation, but when we talked about polar coordinates, we represented x and y in terms of r and theta. And we went through an argument of talking about the polar rectangles and coming up with the volume of the polar rectangles. Well, when we did polar coordinates, our dy dx became r dr d theta. And that r that we have in our integrand in polar coordinates is the Jacobian for the transformation from rectangular coordinates to polar coordinates. So the r is our Jacobian. If we did these partial derivatives for polar coordinates, we would come up with our Jacobian as r. And then our new variables are r and theta. We did the same thing with spherical coordinates with a triple integral. And we had this quantity rho squared sine phi in front of our d rho d phi d theta. That rho squared sine phi is the Jacobian for the transformation from rectangular coordinates to spherical coordinates. So we've worked with this idea before. we're talking about a little more general, we're going to talk about some more general transformations that we can do using the Jacobian. Those are specific examples of Jacobians. So the video that I talked about before, this 14.8 supplement, gives some motivation as to why the Jacobian takes this form. It has to do with approximating areas with a cross product, similar to what we did for surface area. And that gives a little talk about why it comes out this way. So, questions so far about what we're talking about. So this just gives us a way to do a general transformation to change coordinates, to change variables, if we need to for a specific situation. We'll talk about what those situations might be, we'll do a couple of examples with our Jacobian. All right, so I just want to do an example of finding a Jacobian. We'll be given a change of variables and find a Jacobian, and then we'll do a couple of examples of why we might want to do a change of variables for a specific kind of integral. All right, so let's look at a couple of examples. So let's say we're given a change of variables. We want to find the Jacobian for these problems. So we have x equals negative 1/2 u minus v, and y equals 1/2 u plus v. So somehow we came up with this change of variables. We want to use this change of variables, and we want to find our Jacobian. So we're gonna evaluate our Jacobian. So our Jacobian, just to write our symbol, dxy duv, and just a reminder, it's this determinant, dx du, dx dv, partial of y with respect to u, partial of y with respect to v. So I'm going to plug in my partial derivatives into this determinant. Well, partial of x with respect to u is minus 1/2. The partial of x with respect to v is positive 1/2. Partial of y with respect to u is 1/2. Partial of y with respect to v is 1/2. I evaluate that determinant, and I get minus 1/2. So if we were using this change of variables, we would have this factor of minus 1/2 as part of our integrand. So Jacobians are easy to calculate. Sometimes finding the change of variables can be difficult. But let's look at a little more complicated one. Let's say that x equals, yes? Partial of x with respect to u. So x is negative 1/2 u plus 1/2 v. Take the partial of negative 1/2 u. I just get negative 1/2. Oh, when I do the determinant, so negative 1/2 times 1/2 is negative 1/4 minus 1/2 times 1/2. 1/4 equals negative 1/2. Sorry, I thought you were talking about this negative 1/2. X for this one, x equals e to the u sine v, and y equals e to the u cosine v. And we want to find our Jacobian for this particular change of variables. So our Jacobian is going to be the determinant. Our partial of x with respect to u is going to be e to the u sine v. The partial of x with respect to v is going to be e to the u cosine v. Partial of y with respect to u is going to be e to the u cosine v. e to the u cosine v, there we go. And the partial of y with respect to v is going to be minus e to the u sine v. So we evaluate that determinant, and this comes out to be, we multiply these two, multiply those two, subtract, we end up with minus e to the 2u. So if we were using this particular change of variables, we would have this quantity, minus e to the 2u, as part of our integrand. Just like we have the r in our integrand when we use polar coordinates, or the rho squared sine phi when we use spherical coordinates. Same kind of idea. All right, are we good with calculating Jacobians? All right, let's talk about a region and why we might want to change variables to evaluate an integral in this region. Okay. So we're given our transformation. X equals 1/3 4u minus v, and y equals 1/3 u minus v. And the region, I'm going to do a sketch of the region. So we're given this region, and we need to, for this problem, we're thinking we're going to have to evaluate an integral over this region. So here's our region. And we need to evaluate a double integral over our region. So to evaluate a double integral, just to think about what we'd have to do, if we use vertical rectangles, we would have to set up an integral for this portion that goes to here, another integral from the portion to this point, from this point to this point, and another integral from the 0.41 to the 0.63. So we'd have to set up three different multiple integrals. Same thing if we went horizontal rectangles, we'd have to divide it into three integrals with these line segments as our boundaries. So we want to try to simplify this. So here's our region in the xy plane. What we want to do is sketch the region in the uv plane. So we want to see what our new region would be after we do this transformation. So similar to what we do with polar coordinates, where we sketch our region in the xy plane. With polar coordinates, our region, when we use polar coordinates, our region is usually a circle. So the transformation is not that much different. So here we're going to sketch the region in the UV plane. So what we're going to do is solve this set of equations for u and v in terms of x and y. So we're solving these equations for u and v in terms of x and y. And then we can go about finding our region in the UV plane in a couple of different ways. So from this first equation, I can rewrite this first equation. I'm going to call this equation 1 and this equation 2. From equation 1, we can say that 3x equals 4u minus v. So I'm going to solve this one for v. This one tells me that v equals 4u minus 3x. Now I'm going to substitute that into 2. Substitute that into equation 2. So I get y equals 1/3 u minus 4u minus 3x. And I solve this one for u. This tells me that u equals x minus y. And now I can substitute this back into the first equation. Yes? Oh, yes. Thank you. Now I'm going to substitute this back in right up here. Substitute this in for u, and I will get v in terms of x and y. So substitute this in here. So v equals 4 times x minus y minus 3x. So this gives me that v equals x minus 4y. So what I can do now is I'm going to take the coordinates of my vertices of my region in the xy plane, substitute them into these two equations, and I get the vertices of my region in the uv plane. So I'm just going to make a little table here. So I'm going to substitute my vertices in. So at 0, 0, when I substitute these into these two equations, I get the vertex in the uv plane is 0, 0. When I substitute in the point 2, 2, I get the vertex in my uv plane for that particular one is 0, negative 6. When I substitute in 6, 3, for my new vertex in the uv plane, I get 3, negative 6. And when I substitute in 4, 1, I get the vertex 3, 0. So now I can sketch this new region in the uv plane. So let's sketch this. This is V, and this is U. So I have a vertex at 0, 0. I have a vertex at 3, 0. I have a vertex at 0, negative 6. And I have a vertex at 3, negative 6. So here's my region in the UV plane. So I'm going to call this region R. And I want to undo that because I'm going to write some other things there. This is region R, and this will be our region S in the UV plane. So this transformation turned a parallelogram into a rectangle. This region is much easier to integrate over than this parallelogram in the XY plane. So we've transformed a parallelogram to a rectangle. Now let me give you some motivation as to why, before we go on, questions on what we did here to find our region in the UV plane. Solve these in terms of, for U and V in terms of X and Y, and I just substituted in points for my vertex. Let me give you some motivation as why this was the transformation for this particular region. If I find the equation of this line for this boundary, that boundary, the line is y equals x, or I could write that as x minus y equals 0. The equation for this line is, I can solve by, find the slope, use point slope form. I can write the equation of this line as x minus y equals 3. Well, we made the substitution u equals x minus y. My region is x minus y goes from 0 to 3. U goes from 0 to 3. X minus y equals 0 to x minus y equals 3. If I find the equation of this boundary, I get the equation is x minus 4y equals 0. The equation of this boundary is x minus 4y equals negative 6. V is x minus 4y. X minus 4y, V goes from 0 to negative 6. So that's where these transformations came from, was from the equations of the boundaries of this region in the xy plane. That's how we made that substitution. And written this way, x equals 1/3 for u minus v, is solving these two equations for x and y in terms of u and v, doing the reverse of what we did here. So that's why in this problem we chose these transformations, because the boundaries of my region give me these equations. So if you have a nice region where you have these parallel lines, you can do this with more complicated regions, where you have these parallel lines or these functions on either side that give you nice constants as their boundaries. That gives you a suggestion for how you want to do your substitution. All right, questions then? All right, let's go through a problem where we want to evaluate, we're going to evaluate an integral over a region. So we want to evaluate the integral of R over our region R of 60xy dA. And we're going to be given our change of variables. So this is similar to the one that we did the example for. And here is our region. So these are the vertices of our region. And I don't think my drawing's not going to turn out perfect, but we'll get the idea here. So my points aren't exactly where they need to be. This should be either a rectangle or a square. So here's my region in here. Oh, and this point is 1, 0. So I can go about this a couple of different ways. So the first thing I'm going to do is solve this system for u and v in terms of x and y. So from my equations, I'm going to rewrite these. I have 2x equals u plus v, and negative 2y equals u minus v. So I'm going to add these two equations. When I add these two equations together, I get u equals x minus y. When I add these two equations, I can subtract these two equations from each other. When I subtract these two equations, I get v equals x plus y. Well, let's look at the boundaries of our region in the xy plane. If I find the equation of this segment, the equation of this segment is x minus y equals negative 1. The equation of this segment is x minus y equals positive 1. Doesn't look like it, but they are actually parallel. The equation of this segment is x plus y equals 3. And I can find that using the points. And the equation of that line segment is x plus y equals 1. So for our region, u, x minus y, is varying from negative 1 to 1, and x plus y is varying from 1 to 3. I could go through the process I did in the last problem of substituting in the coordinates of my vertices, or I can find the equations of these line segments and look for these constants. So from our region, I get negative 1 less than or equal to u less than or equal to 1, and 1 less than or equal to v less than or equal to 3. So my new region in the UV plane is u is from 1 to 3, so there's 1 and there's 3, and v goes from negative 1 to positive 1. So there would be my region in the UV plane. Did I do it backwards? V is from 1 to 3. Oh, yep. So I sketched my region backwards. Double switched my variables. So v is 1 to 3, and u is, let me switch this around, 1 to 3, and v is negative 1 to 1. So there's my region in the UV plane. And I need to calculate my Jacobian, dxy duv, and I get the discriminant similar to what we did, similar to the example we did before. My discriminant, my partial derivatives are 1/2, 1/2, negative 1/2, 1/2, and this evaluates to positive 1/2. So now I need to substitute my x and my y in terms of u and v into the integral. My Jacobian is 1/2, and my limits of integration are negative 1 to 3 on v and negative 1 to 1 on u. So I'm going to substitute this into my integral. So the integral over r of 6dxy dA is the integral from 1 to 3 negative 1 to 1 of 60 times 1/2 u plus v times negative 1/2 u minus v times my Jacobian times 1/2 times the u dv. And when I simplify this, this comes out to be the integral from 1 to 3, integral negative 1 to 1 of minus 15 u squared minus v squared, and my Jacobian 1/2 du, sorry I forgot my v here, uv. Not a difficult integral to evaluate. I end up evaluating this integral in terms of polynomials. And when I evaluate this out, it comes out to be 120. So that's our process for evaluating an integral using Jacobians. Now these regions that we talked about here where we have nice straight sides, not particularly complicated. They make the integral very difficult, not difficult to do, but just kind of tedious. We can also transform different kinds of boundaries. Just want to sketch one really quickly. Say we had a region in the xy plane where we have these hyperbolas. That one, I want to make these. So say this was our region in the xy plane. And this is xy equals 1. And this is xy equals 4. Well, we can make a change of variables where u equals xy. And let's say this is y equals 1 and this is y equals 3. Here we could say u equals xy and v equals y. So my change of variables would be u goes from 1 to 4 and v goes from 1 to 3. So I could transform this region into a rectangle in the UV plane using the boundaries of the region to pick my change of variables. We can also use Jacobians to change variables when our integrand is difficult. So we can change the variables to simplify our integrand. Similar process. All right, homework. All right, there you go.